today I would like to talk to you about another completely unpredictable topic, namely modeling and estimating performance in Ceph clusters. And you may wonder why I'm here from SUSE, because you may know us as a Linux vendor and not so much yet as a storage vendor, which is actually not true. We have been supporting and shipping Ceph as part of our OpenStack cloud offering for a while, and since about February, we are shipping it as an independent product called SUSE Enterprise Storage, which is based on the Ceph distribution. And we have a growing team, and we have plenty of open positions, which is me being the engineering team lead is currently the most pressing issue I have at my hand.
En wat krijg je erbij dan? Wat is het voordeel?
So, just before I get into why I'm giving this presentation, I would like to go really quickly over what is happening. Besides that, before I'm not going to do any marketing blurb here. If you have any questions regarding our product offering, please come see us at our booth. I'm working in engineering, I'm not a marketing or sales guy. What is Ceph? Many people here will already know it, but just if this is your first exposure to Ceph and to the Ceph community, I just want to cover it. So Ceph is an OpenStack distributed storage distribution. It's the most popular choice for OpenStack, but it's also useful for many other scenarios like archival, backup, media archiving, things like that. It has a lot of goodies, distributed object store, which is an underlying technology called RADOS. It has built-in redundancy, mostly very efficient scale-out, which is a topic that we are also working on in engineering. Can be built on commodity hardware, which is a big plus. Instead of having to purchase expensive appliances, you can now purchase plenty of cheaper and in the end just as expensive hardware and deploy this in your own data center. But in the end, the goal is to have lower operational costs and makes the storage offerings that you have more flexible and more scalable. Ceph can go where other storage solutions in the past just could not go. There was only so far how you could scale a single box unless you spend a real lot of money to buy a much bigger box. And with Ceph, all of this is very possible. Thank you. So from 1,000 meters closer, you will see that Ceph underneath it is actually based on RADOS, Autonomous Redundant Storage Cluster, which you very rarely as a user or even as an administrator interact with directly. Normally you will be accessing this data that you have in your Ceph environment through either the object storage interfaces like Amazon S3 with RESTful interfaces, as a block device if you're mapping this as an RDD or RADOS block device to a Linux client, or possibly even as a file system, even though that's not yet something that we would recommend for production use. Except in very limited circumstances. And for example, if you use it for hosting virtual machines, you're essentially using the block device layer through the user space integration with security. So that's one of the most well-tested access patterns. And as you can see here, also it supports things like rather sufficiently large block devices for most virtual machines, like 16 exabytes, which I admit we haven't yet fully tested in practice. It has SID provisioning and snapshots. So it has all the features that you would look for and plenty more. But actually this presentation is not so much about Ceph itself. But still, on the setting the stage here, Ceph does not store the data, it distributes the data you give it, and it doesn't store it all on one node. It distributes it across multiple nodes in multiple copies. And on each of those nodes you have typically plenty of disks. You use local disks, not network attached storage or anything like that. And there you have, eventually, you have a physical disk, or maybe nowadays you have an SSD or flash, but still, somewhere the data actually has to be stored on physical hardware. Then you have a file system in between, XFS, ButterFS, X4, and on top of that, the OSD. This is actually the first part of the Ceph storage stack that comes into play here, which manages the data assigned to one single disk in the cluster. Those OSDs serve the storage to the client themselves and handle recovery. You have many of these in a single node, probably more than I can show on one slide. Yes, one more. And you also have, besides OSDs, you have monitors which manage what data the current configuration and layout of the cluster. So And when you bring all of this together, you have, say, 3 monitors, which is a typical number, a bunch of nodes with lots of disks, and you have a small Rados cluster. I didn't show here anything else like the router's gateway if you actually want to use it through S3 interfaces or the metadata service if you want to use the file system. So here you can see the basic idea. Ceph takes the data, chops it up into various chunks, and then distributes this across the nodes. There's a topology map, so you can specify which data should go where. So to make sure that not all of your data ends up on the same node or even on the same disk with all 3 replicas, which would be, sort of pointless. And you have basically on the Ceph storage layer, you have 3 conceptual components, actually 4, which is on the next slide. You have pools in which all the data is stored, so you have a cluster, you configure several pools, and into those pools you actually store the data. And you have placement groups, which actually end up on the OSDs. If you're familiar with Linux volume management, you can think of the placement groups as a physical extents on disk. The pool is essentially a volume group, and the objects in there are sort of like the logical volumes you have on LVM. And Crush is basically the heart of the Ceph storage, which is a deterministic centralized placement algorithm, which is distributed hashing based. It's Sage PHP thesis. It's a really impressive read if you have the time. But at the end of the day, mostly you can assume it's magic that just works. And if it doesn't work, it will call Sage. So, pools, like I said, is a logical container for the object. I originally was hoping to skip through this a lot faster. So, the placement groups are sort of important. Just to keep in mind that it maps an object to placement groups, then distributes these to the OSDs. A PG typically exists on several OSDs for replication purposes, because you don't want just one copy of your data, and one OSD typically is host to many placement groups. Again, let's skip that a little bit. Okay, so this is actually an image of an object made of several components, and the Ceph project would chop this rubber duck and assign it to many parts in the pool. I'm a big Lego fan, so I like the saying that you can deconstruct this and then turn this around, but typically if you take a block device, it will be distributed in 4 megabyte chunks. So if you count all of these objects times 4 megabytes, it would actually be a really big rubber duck. So this object itself would end up on a much smaller environment. Here's just showing the interaction. When you want to actually access one of those objects, you end up seeing Ceph maps this to the object ID and the placement group, and then the Crush algorithm knows where the data is. It will write, for example, when you write the object, it will write it to one OSD, the primary OSD, via the public network, and then replicate the data as often as needed, or in the afternoon as we'll hear about how that works with the radio coding, to the other nodes. This does not happen over the public network, so it's not the client that actually sends the data thrice or twice or how often to all the OSDs where the data is stored, but this is happening internal to the Rados cluster. And reads are currently mostly handled similarly, so you don't actually get, you don't actually stripe reads across all the OSDs. So in theory, I guess one day you might be able to. So,
okay.
So, and given that we are now building storage systems from commodity hardware with commodity software, customers have completely unreasonable expectations sometimes, right? Yes? Can we all agree that those are completely unreasonable expectations for a customer to have, right? You have all those various things that play into this, and we'll cover them some more. But mostly customers want to know in advance, before building a 10 petabyte storage environment, how it will perform and how they should build it, and what will happen to their system once they make a certain change. And if I build it like this, what will the characteristics be? How do I need to build it if I want those specific characteristics? And so when I was in Boston 2 weeks ago at the Vault conference, there was one saying, at the end, all the storage engineers, they wanted one t-shirt. It said, it depends, right? If you talk to a software engineer or even a hardware architect about things like this, you go like, Oh, that was a bit too early, but can we? I didn't actually see the slide. Anyway, so there are so many expectations that it's really, really difficult to know in advance how the performance will be. And I will. Yes. Now we can go on. Thank you.
Het is moeilijk aan management verkopen, toch?
So
It depends. Het is moeilijk aan management verkopen.
Is that you try to understand receiving end, many requirements that we get are not entirely clear, so we spend most of the first time clarifying the requirements. You make a best guess based on the current best practices. You build a pilot, and you refine and tune this until the desired performance is achieved, and then you scale this up, right? So that's how you would normally do this today. It's a very iterative process. For some very limited use cases, like we'll be hearing later on, it's possible to pre-package hardware, but then you have also constrained a lot of the flexibility that the Ceph cluster gives you, which may exactly be what you want, because if you have too much flexibility, it's going to come back and bite you. So let's talk a little bit about the various performance aspects of the, yes please, go on, of the software-defined storage stack. So first, contrast them with a legacy storage array. The limits, you have a tightly controlled environment, limited scalability, you typically have few options. If you go to one of the big vendors, you get the choice of one. You know, I will build every car for you as long as it's flat, right? So, or typically maybe you get the choice of disk drives, maybe you get to choose how much cache the controller will have, maybe you get to choose, you know, gigabit, 10G, 40G, InfiniBand network, but you very rarely have influence over the CPU you get, you know, and all those things. The benefits of this are that it's actually reasonably easy to understand, you know, and we have been deploying network-attached storage area network for so long that we actually know or have a gut feeling of how these work. You know if you build a system like this, it's over-spec, but you know it will work. And you have somewhat deterministic behavior and pricing. Even though the pricing may be higher than you would like, it's still somewhat deterministic. Okay. So when you go to software-defined storage, where you control the hardware setup that you build, and the software configuration, the limits to the flexibility are, we don't know. The benefits are, we get infinite scalability within, you know, physical limits. You can adapt it to your use case as much as you like. You get infinite choices, you can adapt it to whatever you want, you have infinite flexibility, and what could possibly be wrong with that, right? So, actually, there's a lot of things that makes this very, very challenging in practice. Because when people even say performance, right? An engineer will come back and say, performance, what exactly do you mean? Do you mean throughput? Do you mean latency? Do you mean I operations per second? Are you talking about a single client or about the cluster as a whole? Capacity, are you talking about capacity you can fit into a rack? The total capacity, density. Then we have softer factors like availability of the array, which is easy. Everyone wants the array to be always up, which is hard in practice. Reliability, safety is an issue. Safety like data exposure, so safety all those external factors. And of course then they have to be cheap. Cost is always a factor, adaptability and flexibility. How can you scale the system up in the future? How can you go about upgrades? All these things play a role. So when you say performance, an engineer will say it depends, right? So you have to make a lot of trade-offs here. Can you go on, please? And the problem is, these goals conflict sometimes. It's hard to build a system that is optimized on all axes, right? For example, availability versus density is a big issue. If you have, a perfectly dense system where you have the maximum capacity in an array means you have as little redundancy as possible, because redundancy consumes overhead, meaning you get less density. I/O operations versus density. So this one is, again, not as clear-cut. If you have dense data, it means you can also access it fast. But it also means that maybe if you only have them on a single spindle, or if you use something like SMR, single magnetic recording, those new drives that aren't actually random access, you get very good density, but I/O operations per second depending on, another dimension, you can read them really fast, but writing is difficult. So again, I/O operations for read or for write, or for, for specific kinds of writes, it gets really complicated. Latency versus throughput, and of course everything is opposed to cost, right? There's no way how to build any system that's free. There's no free lunch. So you have many hardware options, many choices, many decisions that you have to make. So a multitude of choices. Okay, go on please. So let's start, highlighting a few of these. Network is reasonably easy. Networking is one of those few areas where, as things go faster, latency goes down within reason. You have physical signaling limits, but still. It's also easy to say, okay, you should have a public network and you should have a backbone network, so these are easy, and probably an admin network. Cluster network should have more bandwidth than the public network, because obviously that's where the replication and rebalancing and resynchronization takes place, so all of these are reasonably easy. But still, it's important to see that what you do on the public network has impact on the private network. And there again, but still you have a lot of choices, and you can tune them in various ways. For example, when you go to, when you realize that one Ethernet interface is not enough, you go to bonding. And for bonding, you again have multiple choices that, depending on your switches, will have different performance. InfiniBand is high bandwidth, low latency, typically more expensive if you have to buy them as a consumer. They have RDMA support, which will help with latency again. And in practice, InfiniBand has been replacing Ethernet as a networking of choice since the year of the Linux desktop, right? So everyone keeps waiting that InfiniBand will finally take over, but then Ethernet gets faster, it gets cheaper again, and so it seems to be, InfiniBand seems to exist to make Ethernet go faster. Unless you have the money to actually go buy InfiniBand at any given point in time, where it will always be a little bit ahead of Ethernet. So, thank you. On the storage node, again, you get so many choices. You get to choose the CPU, you get to choose how much memory, various storage controls, we'll get back to that one. SSDs for the OSD journal, various types of hard disks that you can add. You can add more nodes, you can have a Ceph cluster that has, say, a petabyte of capacity distributed across 5 nodes, or distributed across 7 nodes, right? So what would be the benefit of that? You get, obviously, as you add nodes, you get more capacity, you get more total throughput, you get more IOPS because you have more spindles, more disks, you can do more, redundancy increases. The latency for a single write is not so much affected unless you were congested before, because you're still going through the same I/O path. And eventually you hit the problem that the switch that you have has only so many ports, and then you have to worry about interconnections between switches, right? Okay. When you add more disk, of course, again, you get more redundancy, more capacity, throughput might increase, I/O operations might increase. Again, you consume internal bandwidth in the node. You may have, higher CPU and memory load on the node. Latency again is mostly unchanged. File system choices also have a big impact on the Ceph cluster. Here I'm just highlighting the two that SUSE supports today. I know that there's theoretically still X4 in the mix, but we didn't do any investigation there. ButterFS seems to be the choice of the future for the OSD file system. It offers very interesting features like checksumming and compression and copy on write. It also has higher CPU utilization and, depending on the workloads, more disk fragmentation. And XFS seems to be the current most mature choice. SUSE has been supporting XFS since, I think, 2000, 2001, I keep forgetting. So it's a long time, we have a lot of experience with it. But still, there are many options that you can tune even at the XFS level. You have various caches in the stacks that affect the performance. Typically, the client-side cache is the most important one. Obviously, it's closest to where the data is actually used. It does not really help with write performance because writes obviously have to reach the backend storage, right? It helps a little bit with aggregation, but in the end, that's where it's bypassed. The server OS cache has pretty little impact, but the caching on the controller itself, on the drives, can have a big impact. Because typically, the backend storage mostly sees writes. The front end, for most workloads, will have cached a lot of the read, unless you're doing a lot of streaming reads. Like if you have a booting of, say, a virtual machine, the client will have cached a lot of the read I/O, so the backend mostly is bothered with writes. Yes, please. With Ceph, you can also combine hard disks with journals on SSDs, which mostly still are very costly, but provide a big performance impact, and the cost keeps coming down, up to the point where some people are now deploying all flash storage, which then opens up a whole other kind of forms and performance issues. They help a lot with, random I/O. At the end, when you may overwhelm the journal, and when you overwhelm the journal, obviously, then you fall back to the write performance of the disk. Because every journal has a limited size, and when you write more data than fits into your journal, then eventually you have to handle the overflow. And they consume storage slots, which lower your storage capacity. And sometimes maybe a large battery back cache on the storage controller can have bigger impact on your performance than having SSDs. So hard drive parameters, I'm just not even going, typically here, the answer is buy more drives, because a lot of the caching happens at other layers. But SMR, the single drives, those will have a big impact. They're not yet perfectly well supported on Linux. There's still work ongoing. Btrfs probably with a copy on write file system that fits very well with how SMR drives operate. There used to be the thing that when I started building computers, RPMs mattered, right? How fast the thing would spin. Yeah. Nowadays, the very high-end drives, you can still buy 15K drives, but they're very expensive, they have low capacity, and in the Ceph cluster they really have no place, because you would rather handle this by having more drives and getting more capacity and more spindles. Because spindles can always be replaced with more spindles. And they also consume more power, which may matter in your use case. Plenty of other parameters when you look at the I/O scheduler on the backend drive. Btrfs and XFS have a staggering number of MKFS options, and of course you can also encrypt your data, which again will have a performance impact. And if you look at how DMCrypt operates, it doesn't just encrypt the data, but it also encrypts the position on the disk, so you get more random access on your drive. So there's that also has a huge performance impact. Redundancy choices, I'm just not going into a lot of detail here now. We'll hear more about this in the afternoon, I hope. But Ceph basically supports two distinct modes of ensuring redundancy. One of them is it will just write out multiple copies of your data, like RAID 1 does, like mirroring does, right? That gives you, potentially one day increased read performance, but it also more copies, lowers the throughput and increase latency somewhat. Because you have to actually write the data to multiple drives, and you have to wait for all of them to complete. Even though you do this in parallel, it takes longer than writing to a single node, because you still have to replicate it over the backbone network. And you obviously, the more replicas you have, the more you consume backend performance on the network. Rebuilds can leverage multiple sources, but it has a significant capacity impact, right? Think about it. You have 2 copies in addition to the primary copy of the primary instance of the data, means 3 copies. That means you have 66% overhead on your data. If you're building a 10 petabyte cluster raw capacity, that means you get about 3 petabyte out of it. And that's, that's a big, big impact. Erasure coding will help with that. I'm not, basically at this point in time, let's say it gives you much better density by saying, you specify, say, 20% overhead while tolerating 2 failures. And that has many, many advantages. The downside, of course, being that you get a lot higher CPU overhead, and during rebalancing and rebuilding, you have a lot of network activity on the backbone. So it's not ideal for actually high-performance workloads directly. Yes, please.
How does that work with when you, for example, have a hardware RAID controller underneath it?
Okay, so that's an excellent question. The question was, how does Ceph work with if you have a hardware RAID controller underneath it? The answer is you don't. With Ceph, the redundancy is handled entirely at the Ceph layer. So if you have a RAID controller, you would be configured in a JBOD mode. Even though, unfortunately, today this is not possible with all rate controllers, and you actually have to sometimes create, if you have 12 drives, 12 RAID 0 stripe groups to actually expose a single disk. Because the hardware vendors haven't yet quite caught up to the software-defined storage thing. Yeah, so you wouldn't normally do this, because with Ceph the redundancy is not node local, but you want additional replication to happen on another node. So if this node fails, you don't lose redundancy. If you were using a RAID controller underneath this in addition, you would be, degrading your density even further, which is very much not cost effective. So
wouldn't it make sense then to use the hardware RAID to use less copies?
Wouldn't it make sense to use the hardware RAID and use less copies? The short answer is no, because then all the copies exist on a single node and not on multiple nodes, and that node fails, you lose all copies that are associated with that node. So, okay. So,
one small question.
One back.
Regarding the cache of the RAID controller.
Right.
Have you seen instances where the caching doesn't solve anything? Doesn't give any performance benefits?
I've not seen a cache never give any performance.
Well, any, but I mean significant then.
Well, yes, so if you have a cache that is not battery backed, you cannot use it for write caching, and then you don't get
battery backup.
If I have a battery backed cache, I've always seen significant performance impact so far in my testing. Actually, when you monitor it, you can actually see the cache filling up. You get a lot of performance while the cache is still filling up and eventually drops down. So,
but still you get the benefit of the head placements.
Yeah, you still get benefit of that, and you get a lot of write aggregation. And so yeah, the cache in the controller always seems to help. I wish I could buy more cache in my controller sometime. So,
okay, thank you.
Sure. Cache tiering is a great way to combine the two. With Ceph you can have multiple tiers of pools, one pool tied to the other one acting as a cache for the other one. You can have a fast replicated cache, say on SSDs or flash architecture, with an erasure-coded pool on the back end, and I'm pretty sure that's also going to be covered in the erasure coding presentation this afternoon, because there's some ways how you cannot otherwise use erasure coding directly. You can't use erasure-coded pools for everything directly in Ceph, because erasure-coded pools don't support all the features of a normal Ceph pool. But the cache tiering is a great way of combining this. So, but it comes with a lot of parameters to tune. And then there's placement groups where you can configure how many you want in your pool. So basically, this was meant as a tour de force. It wasn't intended to actually go into any of these. What I wanted to show you is that there are very many factors that affect the design of such a system. And those are all the individual components. When you assemble them to a system, many of those individual components seem straightforward enough, right? So more cache, good, right? File system one faster than the other. RAID controllers, different performance, Seems straightforward. But the interactions are not. There was this one, I spent a lot of time reading benchmarks last year. And there's this particular benchmark of which I would just like to present you this slide. It's a very straightforward benchmark performed by a colleague at Tang, where the benchmark various RAID controllers in various settings. How do I attach those, what performance do I get out of my RAID controllers for a given workload? And you can see that the RAID controllers stack up differently in different workloads. I just grabbed one of the slides out because it was the most obvious one. And you can also see that we have this other dimension of file systems. This combines the performance of a RAID controller with that of the file system. And unfortunately, it turns out that not just the RAID controllers are faster than the other, or the file system is faster than the other, but if you compare the first one to the third one on that list, right, you will see that for the first one, the RAID controller overall is faster on average, with BufferFS having a huge lead, and on the third one, with a different RAID controller, which is overall slower, the file system performance relative to each other has reversed. If you had been able to predict this, I would really love to talk to you about having a job. Put this to an engineer, he will go like, yeah, of course, because, I can explain after I've seen the benchmark, I can say that they have slightly different timing, and they affect, how, that affects how the file system is able to aggregate the writes, and they have slightly different timing on the bus, and CPU utilization and memory utilization for the file system, and combined they have this impact, but it's really, really hard to predict things like that. So you build your cluster, right, and you think about it. If you had only seen the benchmark for, say, Btrfs, right, and you were on this, say, on the force controller, right, for example, and you go like, my file system performance is not good enough. Let me buy a faster rate controller. And you buy the third one, and suddenly your cluster performance cuts in half, right? That's not something that you would expect, right? So what we really need, benchmarks they are isolated. They are not standardized workloads. A huge variety of reporting formats, and as an engineer, it drives me crazy that they are all, you get benchmarks when somebody wants to sell you something, except like the very excellent ones we've seen before. But in general, somebody wants to highlight why their product is better, so they neglect all the other cases, right? And that means you get a huge variety of reporting formats, selective reporting, and mostly graphs. Very rarely we get raw data out of the benchmark. And they are, typically skewed to highlight the superior performance of whatever new product they want to sell to you. You don't have enough data points to actually make sense of the why the benchmark works like that. Not enough data about the environment, and unfortunately, mostly from lab setups. Very rarely do you get to run benchmarks in production environments, which I, as an engineer, would really love to have, because no one runs a lab setup. Setups are always loaded. The setup is never completely idle. So there are some ongoing efforts, like Ceph Earth has been ongoing for a long time. The final death nail seems to have been when it was merged upstream. Before that, there was some activities and it was merged upstream, and the last update to the Ceph Earth code base in Ceph was unfortunately a year ago. Ceph Earth is a project from Intel, where I've so far unfortunately not yet been able to see a lot of code. And it seems to be in some ways focused on object storage and measuring the internal aspects of Ceph. So basically, this is what I'm currently working on as an engineering task. Is I want a standard benchmark suite for Ceph that gathers a lot of relevant data from the cluster. Here on the next few slides, I would also outline what they are, but given that we are a little bit pressed for time now, I will not bother you with that. But basically, it would benchmark things like the network connectivity between the OSDs and the client nodes, between the OSDs and the monitors, between the clients and the monitors. You get the idea. Throughput and performance, throughput and latency, and would also run benchmarks on the individual disks, so you can compare the benchmark of an individual disk and extrapolate that to the whole cluster. There would have to be core and optional tests. The core tests that you can always run, but obviously a lot of benchmarks. You won't always be able to get 8-hour slots for benchmarking on your production cluster, but you may be able to get 5, right? 5 minutes, And also non-destructive tests would be part of core, because the goal would be to be able to run this on existing Ceph clusters. So you can also track the evolution over time, which again as an engineer and even as a data center operator is really interesting to you, because maybe this kernel update was not so good for your particular configuration. Technically impossible for any vendor to test all possible options. Your environment will always be special in some way, right? Unless you really get everything down to the firmware version exactly as it was in the lab, there will be differences, and that makes it really hard. So you need to be able to track regressions and also compare them. But frankly speaking, no human is able to make sense of the data that is Ceph cluster. There are very few exceptions that you can make some heuristics, but the overall thing, like the slide I just showed you, are just not, brains don't work like that. We assume that mostly human brains have limitations. They tend to think in cause, effect. But multiple causes and overlaying effects are not something humans are very strong on, unfortunately. Otherwise, the world would be a very different place. There's a bunch of ideas here in the slides that we can talk about. Again, go further. One more. And hopefully then, of course, we would like to be able to run this in different Ceph configurations, or even allow benchmark suite to deploy different configurations directly, so you can test with only half of your OSDs or all of your OSDs. Boot the kernel with less memory available, so you can simulate memory pressure. So all those things, if that's possible. And then also you may be able to run something like Performance Copilot, which is a tool that observes the performance of a given system as a benchmark is run. It will gather some things like memory pressure, CPU utilization, all these things. And these things have several problems. It's basically impossible to gather resolution so fine that you really can spot the instruction level. That's more like what Ceph Earth is setting out to with having trace points in the Ceph code base itself. But still you would be able to see something like, oh, I was running at 100% CPU utilization on the monitors for 5 minutes. That's probably not good, right? So even though it's not yet showing on the benchmarks that you're running, you would still be able to spot points of congestion in the system. And again, create pictures. So you can, for example, really see when you run Performance Copilot and you have a disk cache, you can see that the disk utilization will be very high, or the observed write rate of the OS will be very high while the cache is filling up. And then after like 1 or 2 gigabytes, it suddenly drops to essentially down to disk speed because you're overwhelming the cache, right? So this actually allows you to inspect the system in more detail. So the goal basically is to have a holistic exploration of Ceph cluster performance so that you actually will eventually be able to answer those customer and partner expectations, for which we currently have guidelines but not real answers. Machine learning is very interesting here. And this is also a useful data tool for grad students. I know the Ceph community has a lot of universities that are participating, and if you give grad students data, eventually papers will fall out, and some of those papers will be useful. So the idea really is we need more data. So given that we are working on big data, it's actually quite impressive how little data we have on big data, right? And I really would like us all as a community to overcome this by supplying more data to the community and providing it back. And if you have benchmarks, right, I would love to hear from you which benchmarks matter in your environment, which benchmarks you found useful, and especially also which benchmarks were not useful for you, because that helps us to prune down the list of benchmarks that we have to run. Maybe we have, just 1 or 2 minutes for direct questions here, please.
You talked about the crush algorithm that is based on hashing and topology of the cluster. What is the effect of adding or subtracting one node? Will the whole cluster be rebalanced? Okay,
so the question is, what's the effect of adding a node or removing a node? Will the entire data set be rebalanced? And no. So some data will be rebalanced, but crush is mostly persistent. But obviously you want some data to be shifted because, especially when you remove a node, you have to rebalance the data that node hosted. So Ceph, as a crush algorithm, will allocate new OSDs, will allocate the placement groups to new OSDs and vacate the nodes that you're about to remove. If you set the weight of a node to 0, it will shift all data that is on the node to others. And if you add a node about a similius, that's a little bit harder to predict depending on how overloaded your nodes are, but only a subset of the data will be shifted, will not shift all data. That would be very much impractical in a multi-petabyte cluster. Okay, so the question is, have we seen performance degradation with using on-disk encryption? And the short answer is no, because we have deliberately not tried it. Because most vendors that we know that want to run disk encryption are doing this because they want to be able to, it's not actually a protection against attackers that attack the running system. It's an attacker, it's about being able to throw the disks away and wipe them. Some of those customers don't trust, for some reason, there have been some disclosures in the last few years, they don't trust the on-disk encryption. So they rather they don't want to trust the hardware. And they don't want to be tied into a specific hardware vendor that supplies that particular set of encryption. So they want to run encryption in software and never have the disk see unencrypted data. So that's why we haven't even bothered. So the question is, are the Ceph systems running on software encryption? And the short answer is yes. So Ceph Disk supports setting up encrypt on the device map-based encryption on Linux. The key management for this is not yet quite as nice as it should be. but that's for us at SUSE, it's one of the primary features that we want to have in our next product generation, to have the key management easy, because this is a key requirement we see from large customers and partners. So, yes, and
what type of applications for which it would be a good choice to use Ceph for storage? You mentioned, like, for example, the backup, Ceph, but what would not be a good application?
Okay, so you were asking about what is not a good application for it. Okay, so this is a little bit biased. So our focus right now, so I spent the last 50 years before I started doing Ceph doing high availability systems, so I'm a very conservative guy. So we start small. We think that Ceph is very well suited for object storage, for hosting virtual machines, for archival, active archive, media streaming. We don't yet see it competing with use cases where we would currently deploy something like Luster, so high performance file systems, low latency work situations. Low latency is not such a good workload for Ceph, and especially if you need single thread performance. If you have single clients that needs maximum performance, Ceph is, depending on how your client is architected, it's not the best choice, because Ceph gives you excellent and pretty impressive throughput aggregate performance as a cluster, but single thread workloads are not so well suited. And like I said earlier, we don't yet trust the file system in production either. There's still some technical parts missing, like file system check, which if you deploy a file system in practice, you really want to have file system check. So yeah, so that's the workload that we currently don't do. Object and block are fine. File system is coming. So, and with that, please see me at lunch. I need to hand it over to Peter.
Thank you, Lars.